So before we do any of this, I'm going to start by going over just some of the properties of an exponential graph. So an exponential graph, you guys have maybe heard the terminology, and if you haven't heard it, you probably heard it and just didn't know, and you'll probably start noticing it more. It doesn't happen super often. But if you've ever heard the term exponentially, like, yeah, they were exponentially better this year, or they were, the food was exponentially better, or exponentially worse would be the opposite of that. When people use that in normal, like, speaking language, it just means a lot. They were a lot better. The food was a lot better. It was a lot worse. But the reason it's that is because an exponential gets really, really big, really quick. So for instance, one example of an exponent problem is if you start with a, well, I guess we'll do this as a number. If you start with 1, so we have a 1 right here, and then we're going to double that. That gives us 2. That's not that big of a jump. But then we'll double that and we'll get 4. Well, it's a little bit bigger. Not that big, though. Then if we double that, we get 8. Then if you double that, you get 16, then 32, then 64, then 128. Pretty soon, you're getting pretty big pretty quickly. Like, all of a sudden, you're doing 100 in one jump, and then 1,000 in one jump. So that's what an exponential is. That's what they say when they say exponentially, it means a lot, is because it gets pretty big pretty quick. So this is a very good example of an exponential, and we will go over a little bit more in detail about that. That's a good example of what an exponential is. So here's a couple things I want to make sure you realize. I guess really quick, and I guess I should say this is the overall shape of an exponential graph. You can look a little bit over that in a second, but that's the general shape of an exponential graph. It can be a little bit different. I mean, it's the same idea of the shape of a quadratic is that U-shape. That obviously that U-shape can be bigger or smaller or wider or skinnier, but it's all that U-shape. Same thing with an exponential. This can be a little bit different, but generally they're going to look like that. Now, one big thing I want to make sure you realize with this is that, so this example, I started with 1, and I doubled it, and then I doubled it, and I doubled it. So what if we went backwards? What if we started over here? And this is not like the greatest of examples, but if we started at 8 and cut it in half to get 4, cut it in half, cut it in half, if we kept cutting that in half, no, you'll get a really small number. You'll get 0.00002, but you'll never get to 0. So this line down here to 0. We're going to move it up and down later, but it starts asymptote. I call that cross line. What you do, don't cross that line. Now, again, we'll move that line sometimes, and we'll talk about that in a second. But that's one of the big things students miss with exponentials is when they're graphing. They'll graph their exponential and something like this, like this. Well, you're close, but notice how I cross that line? You can't do that. An exponential, it'll never be on that line. That's that asymptote. They're like, well, wait a minute, so asymptote then over here, so if the graph looks like this, asymptote over here, the answer is no. With an exponential, you're not going to have any asymptote on the other side, because again, if you plug in numbers over and over and over again, the asymptote, the other one, the can't cross line, the horizontal one, you'll never get to 0. No matter what numbers you plug in, you'll never get to 0. You'll never get below that. But the other way, if you keep plugging numbers in, it will keep creeping this way, slowly. We'll talk about this a little bit more when we get into the domain and range of this, but that's a really good intro, because again, one of the things I want to make sure you know with that exponential is that asymptote, that you can't cross that line. Last thing before we start the lesson, that's one way to look at an exponential graph. We're starting bigger and bigger, so it looks something like that. But the other graph, an exponential graph, is the opposite way, where it starts really big and then gets smaller and smaller. Again, it never crosses that line. Notice that. You cannot cross that line. So in about 20 seconds, we're going to talk about this. But the blue one, as you go from left to right, when it gets bigger, that's called an exponential growth. As you go from your left to your right, that's called an exponential decay. I don't know if we'll do any of these story problems. I don't know if we'll have time. But you guys have ever heard of like carbon dating when they find fossils and they're like, oh, this fossil is actually 7 million years old because we did carbon dating. And you're like, what does that even mean? That's actually, I wonder if you guys talked about the chemistry. That's this stuff. That's how they use this exponential stuff for that. So there's an amount of carbon in just about everything. And carbon has a half-life where after so many years it gets cut in half, then it gets cut in half again. Well, just like we said, when it keeps getting cut in half, it's never going to be zero. So they can look at a bone and say, oh, it's got this much carbon, do some mathematics, and then they can figure all that stuff out. So that's the reason they're not just making that up. If I tell you the answer, then I'm probably making it up. Half-life, good stuff. You'll learn about in chemistry. Okay, so let's get started here. This is the first exponential growth and decay, and it's really hard for me. Some people say the base formula for exponential is y is equal to abx, and some people just have b raised to the x. So it kind of depends on who you are and what you want to look at. We'll kind of jump back and forth, but I think you guys will be all right. A intercept. Front is your y-intercept. Your b is the base number. Is the variable. Some people are like, well, that's an exponential. Why isn't this an exponential? Why is that quadratic? Well, that one has an exponent, but the exponent's a 2. It's always going to be 2. It always will be. It's not a variable. This one, the exponent is a variable. That base number is a growth or decay. If that base number is bigger than 1, it is a growth. If that base number is in between 0 and 1, it is a decay problem. Now, mathematical morals has to tell you that it's between 0 and 1 is a decay problem. But if it helps you remember, if it's bigger than 1, it's 1, it's decay. For your base, that's going to be something different. That doesn't have to do with the growth or decay. I will not give you any negatives for that. Class, as long as you remember bigger than 1's growth, smaller than 1's decay, I can do that. You guys know the pre-calculus and calculus, if you can remember that again, that's good. Good enough. So then we have some of these graphs where you're just labeling exponential growth or decay. Don't make this harder than it is. As you go from your left to right, if it goes up, it's growth. It's growth. Now this last one, not too much about this, but notice how this one, I told you that cross line is over here to 0. Notice how this one did cross that and goes down here to -2. That happens sometimes. We'll talk about that. We're shifting and moving some things up and down. For this purpose, it's a growth. It doesn't matter what it looks like. It doesn't matter where it is, not what it looks like. It does matter what it looks like, but it doesn't matter where it is. That is a growth. Now, the next part, if you're given the equation, growth or decay, and this is the thing that tricks a lot of students. Because a lot of students, when we talk about parent functions before, we had the parent function for a quadratic was x squared. The parent function for a square root was the square root of x. But the problem is with a exponential problem, this base number can be anything, and it's still the parent function. So it could be a 2, it could be a 10, it could be a 9, it could be a 4, it could be a 0.7, it could be a 1/2. Base number. That base number is not the same as that number in front. That's our y-intercept. So these next ones, state the y-intercept, and if it's growth or decay. It's 12. The base, again, we talked about earlier. It's a growth. So, okay. not too bad. It looks easier, but it tricks a lot of people because a lot of people look at this y-intercept is 2. There is on this one, or I should say, doesn't tell on this one. If there's not a number in front, the y-intercept is always 1. It's always 1. It makes sense. Remember how you find your y-intercept? You never have any equation ever, and you want your y-intercept. If you saw it as 0 for x, negative. Well, if you put 0 for x in that, 2 raised to the 0, raised to the 0 is always 1. That number, that 2 then, is telling you if it's growth or decay. That is bigger than 1, that's growth. Next one, same thing, they make it a little bit tricky because they put that decimal in front. That's okay, that's still the y-intercept, 0.25. And is the growth or decay, so that's bigger than 1, so that is the growth. Last but not least, again, 8. Your y-intercept is 1. There's not a number in front. This one, the 3/4 is smaller than 1. If you're not sure, you can always divide that. 3 divided by 4 is 0.75, so that is a decay problem. Okay. Too lazy, too easy. A Dre K. Dr. Dre called me. But pretty gangster, so that's why I use that. I was going to say something super important, but I don't remember. Are there, oh, that was what I was going to say. I will say, and I don't know if this is ever going to show up. I might put this, I don't know if it'd be a good extra credit question or not. But keep in mind that this number, that base number, if it's bigger than 1, it's a growth. And the reason I say that is because occasionally I have students that just remember that if it's a decimal or a fraction, they say it's decay. But then they end up getting a problem that looks like this, where it's 5/4. And they think, oh, it's a fraction, so it's decay. Well, 5/4 is actually bigger than 1, so that is a growth problem. So that doesn't happen very often, but I wanted to make sure I say it just in case. Any questions on those before we move on? So hopefully not too bad, but again, we're going to start getting more things kind of thrown at us. So the next thing we're looking at is transformations. Now here's the deal with transformations. I'm not doing a lot of the difficult stuff with this. Mainly because we did it earlier with some other stuff, and mainly with exponentials, I don't think it's as important as quadratics and linear problems and absolute values. It's just some base number raised to the x. Again, that b can be a 2, can be a 0.25, can be a 3, can be 1/3, doesn't make any difference. The only thing on in this class is left to right, up and down. So that's this first one. If you have a number in with your x, in with your exponent, that's left and right. And remember earlier when we did this, I told you that if you go left and right, it's always in parentheses and always seems like it's opposite. So if this is a -4, you're actually going to the right 4. If it's a +10, you're actually going to the left 10. Then the k back here is going up or down, and that one makes sense. If it's +3, you go up 3. If it's -4, you go down 4. That one's not terrible. Now, all this other stuff, nice, the number in front, that a that we talked about earlier, is a stretch or compression. If it's negative, it reflects it across the x-axis. I'm not going to worry about that. I'm not going to give you any of those. For us, that a is the y-intercept. That's what the stretch or compression, the place we see that on our graph is the y-intercept. So as long as you remember that a is the y-intercept, and I'll talk about it, but you do not have to worry about those reflections. So the first type, just say, describe the transformation. Again, I'm not saying that this is easy because it's very, I guess I should say, in my opinion, it's easy, but it's very easy to confuse as well. I have seen people that are very good students that miss all these just because right before they take a test, they accidentally forget left and right and up and down, which one is which, and they mix those up. What's the transformation? This one is on the 4 with your exponent, and it's a +4. So if it's exponent, it's left and right. If it's plus, you're actually going to the left. You're That is left. That's the for us right now. Nothing for transformation. That 2 is the base number. It will tell us A, but it doesn't say transformation. Number 10, we have raised to the x minus 6. The minus 10 means we go 6. Again, in front doesn't tell us anything about the transformation. That's the base number. Number 11, we have minus 7, so you go to the right 7, and then the plus 2, you go up 2. So you have 2 of them for that one. And the last one, we have a plus 4 and a minus 10. So the plus 4 is to the left 4, and minus 10 is down 10. Not too bad, but I've had people that mix this up all because they get half credit on every single one of them because they mix around up and down and left and right. So just make sure you're careful with those. But again, the good news is that's not any different than what we did earlier in first semester. It was like chapter 2 maybe, when we took a quadratic and moved it up, down, left, and right, or an absolute value. It's the same thing. Same rules apply. So the next thing we're going to do is we're going to graph these. Now here's the hint that I give you. Graph the y-intercept, the key cross line, the asymptote. Graph those first and then move those. So I've had people that do the opposite way where they try to do stuff first and then find your asymptotes, and it doesn't work really as well. So graph your y-intercept, graph your asymptote, both of those. So for instance, where's the y-intercept? The y-intercept is 1 because there's no number in front, there's no a, so my y-intercept is right here at 1. Asymptote always starts at 0. Transformation. And again, if you want to actually draw out what this graph looks like, it's a growth, so that graph looks something similar to this, just don't cross that line. If you want to start with that, you can. I just think eventually it gets kind of busy when you do that. Do more what that looks like when we're done. So this goes to left 2, down 3. So things that intercept, I go to the left 2, 1, 2, 3. So it's not really a y-intercept anymore. At that point, I move that down. The graph has to cross that. At that point, it's got to go through that order here. And your asymptote, here's the thing. You go to the left 2 or to the right 2 is a horizontal. So going left doesn't change anything. But going down 3 does. So going down 3, you go 1, 2, 3. That's right here. So this is my new asymptote. This is my new can't cross line. That doesn't cross that green line. That goes to that green point. So like this. Really quickly, I should have said this before. Notice how it says sketch a graph instead of just draw your graph or map your function or something like that. The word sketch, not that this is actually mathematically sound or whatever, but for our purposes, if I say sketch, it doesn't have to be exact. It just has to be something real quick that has the general look of the graph I'm looking for. So the things, when you graph this, the things I'm looking for is your y-intercept, or what used to be your y-intercept, your asymptote, that can't cross line, and the general look of your graph, whether it's an exponent growth or decay. Those are the 3 things I'm looking for. So some of you have your graph that looks like this instead. That's fine. I'll still give you points. Line, you go cross that asymptote and go through that other order there to growth. We're good. The other extreme, this line is really steep. It doesn't make any difference. I'll give you full credit on this test. Because again, I'm not looking for the exact graph. I'm just looking for a general outline, a general look of that graph. So number 14, the y-intercept. This one has a y-intercept of 2. And again, the can't cross line, the asymptote is at 0. Then this one, all we do is we go to the left 1. So we go to the left 1. So This is another growth problem. That 3 makes it growth, so we start down here, and then again, we just have to make sure we go through that ordered pair. I guess I forgot to mention, we do move the asymptote, but when you move that asymptote to the left one, again, it's a horizontal line, so it doesn't actually change much. Number 15, there is no y-intercept listed, so that's 1. And then your 0 is right here, your asymptote. So this goes to the right 3 and then up 2. So to the right 3 is 1, 2, 3. Go up 1, 2. That's right here. And then your asymptote goes to the right 3 and up 2. So that ends up being right here. Now, the tricky thing with this one is that it's a decay problem. So make sure you do not draw your graph like this. You get partial credit, but it's a decay problem. So it starts up here and gets smaller and smaller. Don't cross that line. Last but not least, this one, the y-intercept is 2. Looks like in the no cross line, the asymptote is at 0. I move everything down 3, so 1, 2, 3 is down here, and then the asymptote is down 3, so it's right about here. Problem. So goes down. And again, if you're wondering, how do I know if it's a growth or decay? Again, that base number. This number is smaller than 1, so it's a decay. So it's a decay. This number here, not the 2, the base number is bigger than 1, so it's a growth problem. I will say, address this, number 16. If your graph looks like the one I just drew, I'll give you credit for that because you didn't go through the right point, but you have the right point listed on there, so I know. I'm talking about this point right here. But that's why I always say your ordered pairs. Make sure you put those dots on your graph and help you out with that. Technically, I should. There we go. A little bit more of a concept. Last but not least, yesterday when I was teaching this, there was a couple students that got hung up on the idea of your old y-intercept. We're only one step away over here, but over here they were 2 steps away. So how do you know when it's going to be 1 or 2, whatever? The answer is graph them together. Don't do the y-intercept and the asymptote together. The y-intercept, then closer here. Then here is the whole purpose of this y-intercept was 2. So before you even started, they were further apart. This y-intercept was 1, so they're a lot closer together before you start. A lot of people have hung up on that, but I want to make sure I say that, so I don't want people to get confused by that. I know it's been, I've thrown a lot at you, and I haven't asked for any questions yet, or maybe I did, but I don't remember. Are there any questions over this graphing stuff so far? Or any of it, really? It's hard because one thing kind of builds on another thing. Like we talked about growth or decay, and then we use growth or decay for the rest of the time so far. We talked about asymptotes. I guess we didn't talk about. We talked about transformations. We did those. Now we're talking about graphing, so we're needing those transformations. So it does very much build on itself. So the last thing well, there's a couple more things after this, but I'm going to do this, and then I'm going to have you guys do some problems on your own where you pretty much do everything in this lesson all in one problem. State the domain and range of the following. Now, this is what I was hinting at before when I was talking about this graph. You never cross this line. So that's a big distinction. Now, we'll talk about that in a second because the first thing we're going to talk about is the domain. Now, remember, what domain and range mean is the domain and range is asking what x values, or I should say, the domain specifically is talking about what x values are on your function. So, for instance, if I plug in an x value, will that be on my function somewhere? For instance, with your domain, -4 graph right there. So -4 is part of your domain. -2 is on your graph. 0 is on your graph. 2 is on your graph. 3 is on your graph. Here, 4. We have 4 is on my graph. It's just going to be it's going to be 10. Well, yeah, 10 is on there. It's just going to be. What about all other? Yes, this will eventually creep. It just might be a million in the air. But here's the best part. It's all exponential. To be that teacher, if please ask. I will definitely explain it to you. Care, all real numbers for exponential. We are going to jump back to that asymptote. So the graph can go below 0. So the same thing we talked about with your domain. X has a point on my graph. 4 has a point on my graph. 2 has a point. 1 has a point. What about negative 1? Negative. My graph does not go that low on all. Negative 2. There's nothing down there. That means my y value has to be everything bigger than 0. It's above that asymptote. That asymptote is at 0, so it's got to be y greater than 0. Number 18, you can tell we moved this. The asymptote is not down here. If you don't know how to find the asymptote, it's very much where this flattens out and doesn't really touch. If you ever have questions on that, you can ask. That's my asymptote. So the domain first is all real numbers. If you want to write all the words down, you can, but you could also use a shortcut. A capital R that has the 2 downward strokes stands for all real numbers. The range is y, and then it's everything bigger than 2. The graph is above 2, so it's everything greater than 2. And 20, the asymptote is down there. I did not draw that up very well, but you get the picture. It's a -3. So the domain is all real numbers, and this one y, -3, and it's everything bigger than -3 because it's above. Now, this is where I'm going to do a little bit of our callback from what we talked about earlier. Remember what I said, that you won't have any of them that are reflected where they're kind of upside down? Any of them that are reflected? I should have pulled on here, but if I ask you for the domain and range and I give you a graph, there might be some that I make it open upside down. So that way you know that it's not always y is greater than, it could be y is less than. So if it opens upside down, that'd be y is less than domain and range. Any questions before we start these last ones? All right, go ahead and do these on your own. Any questions on those? So, not to shift gears completely, but the other thing that's in this lesson, and I don't know why we picked to do it now, I guess maybe I should do this. It doesn't matter. Maybe it might have fit pretty well back when we did transformations earlier, and I guess we did talk about the graphs and parent functions. But telling me what type of function these are. When I say what type, I mean like, is it a quadratic? Is it a cubic? It is a square root? Is it an absolute value? Is it linear? What kind of graph are these? Now, if you're actually looking at the graphs, 28 through 31, those aren't too bad. But a lot of people get confused by the formulas or the equations. Remember, a linear problem has an exponent of 1. A quadratic is 2. A cubic would be 3. Absolute value has absolute values, and exponential is one we've talked about today, where the exponent is the variable. So 24. The exponent is 4. Now, I know some people that get confused because, well, but we have an exponent of 1 right here. It's always an exponent. This 20. Could be wrong, but I think it's even when you look at the graph. It's a V-shaped graph, so it's absolute value. quadratic. This about this all day. Exponential growth as an exponential. Those four answers are the only options I'm going to make you memorize for a test or a quiz. Honestly, I'll probably make those multiple choice on a test. Because there's four options and that just makes it easier. On a quiz, you might have to know the point, but here's the deal. I'm not going to give you, I guess this is the thing. If someone asks you have to memorize those, and you memorize those four, I guess I should say you'll have a word bank of some sort. This is your word bank. You can use right there. Those are the only four I'm going to use. So I have to try to hit an exponent. Test or quiz, or sorry, a test, I'll probably give you that as multiple choice. Again, you don't have to worry about like, oh, what about a cubic? Or oh, what about a square root? You don't have to worry about that. Those are the only four I'm going to use, and you will have essentially a word bank. So I know this was a lot today. Again, this was one that if it was up to me, it would have been nice to kind of split it up. But we don't have a lot of time to split it up. And overall, this isn't the hardest of lessons still. Again, it's not easy by any means, but there's not a lot of math in it. There's not solving or anything. So if you have any questions, let me know. Other than that, you get started on your worksheet and or your exit ticket. Again, I'm still working on grading those tests.